At first glance, integers, circles, and triangles seem almost too simple to be interesting. But beneath those familiar shapes and numbers lie wonderful patterns and more mysteries, twists, and turns than that Dickens novel. So what happens when we bring these mathematical characters together in a single story? We get the intriguing Basel problem. And for me, the story lit up my imagination. In this video, we will use some basic ideas to solve a problem that some of the greatest math minds attempted and yet failed. Our story starts by imagining you're standing at the origin of a number line. Bend the segment from -1 to +1 into a circle, placing the point 0 at the bottom. We've changed its shape, but its length remains 2. We can watch the same animation, but as part of a bigger process of an expanding circle. But we still highlight the same segment of length 2 where the points -1 and +1 never lose their identities. As the circle expands, it flattens, and every labeled point approaches its home on the number line. We will use this process to prove the Basel problem. Let's replay the expansion and pause each time the circumference doubles. We will call these moments snapshots, not separate circles, but frozen stages in one circle's endless growth. In our first snapshot, the circle has circumference 2. I'll refer to each circle simply by its circumference. Halfway around the circle, we find the two labels, plus and minus 1. Double the circumference to create circle 4. Two new labels appear at the top, plus and minus 2, while the original points are halfway between 0 and 2. Double again to create circle 8. Our focus is the odd integers, which are now plus and minus 1 and 3. Double to create circle 16, which adds 5 and 7. Notice with each snapshot, we double the odd integers. The new integers appear at the top half, and the existing integers flatten to a straighter line. Besides these patterns, there is another hidden pattern. Consider circle 16. Draw a line from -1 through the center. The line reaches +7 on the opposite side. Overlay the previous snapshot. That same line passes through -1 on circle 8. Here it is with physical circles. Align the two snapshots at 0, then draw a ray from circle 16's center through 1 on a circle 8. It intersects 1 on circle 16. And this is not special to 1. Whenever the circle doubles, a diameter through an odd integer on the larger circle also passes through the same integer on the previous circle. In circle 32, the diameter from -3 to +13 also passes through -3 on circle 16. Every odd integer follows the pattern, mysteriously connecting one snapshot to the next. We will return to why this happens later. For now, these hidden connections point toward a remarkable identity. On the left are the reciprocal squares of the odd integers. On the right is a quantity built from a circle. At first glance, these two ideas appear worlds apart. But once we understand the connection, we unlock the key to the Basel problem. The Basel problem asks for the exact value of this infinite sum. This problem was first posed by Pietro Mengoli in 1650. More than 80 years later, Euler shocked the math world by discovering the infinite sum equals pi squared divided by 6. And I'm creating this video because I was inspired by Grant Sanderson's beautiful lighthouse proof. Grant's 3 blue, 1 brown video is wonderful, and I encourage you to watch. But as I studied his proof, I saw another story hiding inside, a story told by an expanding circle. And like Grant, we will place a light at every odd integer and ask, as the circle expands, what happens to their total light? To answer, we first need to understand how the observed brightness from a single light changes with distance. The further away a light is, the dimmer it appears. We'll measure the observed light using the inverse square law. At a distance d, a light contributes 1 divided by d squared units of brightness to the observer. But why the inverse square? First, we'll get the inverse by considering apparent size. The sun is about 400 times wider than the moon, but it is also about 400 times further away. And that's why during a solar eclipse, they can appear the same size. Double an object's distance, and its apparent width is cut in half. However, light radiates in every direction, spreading across the surface of an expanding sphere. The sphere's area grows with the square of its radius. Double the distance, and the same light spreads over 4 times the area, so the observer receives only 1/4 as much. Quadruple the distance, and it spreads over 16 times the area, leaving only 1/16 as much. That is the inverse square law. Brightness decreases with the square of the distance. Okay, place an observer at 0 and a light at 1. As we advance through the snapshots, new lights appear at each new odd integer. The existing lights move further away and appear dimmer, while new lights arrive on the scene. The light sources change, but what happens to the total brightness perceived by the observer? Amazingly, the total perceived light does not change. The observer always receives exactly the same amount of brightness at each snapshot. Consider circle 8. Increase to circle 16 and focus on the circle's right side. Lights at 1 and 3 move further from the observer, so together they contribute less light from the observer's perspective. Meanwhile, 2 new lights appear at 5 and 7. Here is our real mystery. If the total light never changes, then the light lost by 1 and 3 by moving further away from the observer must be supplied exactly by 5 and 7. Somehow, some way, from the observer's perspective, brightness gained from new lights equals brightness reduced by existing light moving further away. The total remains unchanged. I like to imagine that balance as light being passed forward from one generation of integers to the next. But how does geometry enforce this act of conservation? Place the observer at the origin of a coordinate plane and a single light somewhere in the first quadrant. Can we replace this light with 2 others while preserving the same brightness? Geometry comes to our rescue. Draw a line from the observer to the light. Draw a perpendicular line through the light. Where it meets the 2 axes, place 2 new lights. Why these points? The observer and the 2 new lights form a right triangle. Notice the original light rests at the foot of the altitude to the hypotenuse. And this invokes the remarkable inverse Pythagorean theorem, which is similar to the popular Pythagorean theorem, but based on inverse distances. We can apply this to a 3, 4, 5 right triangle. And notice the identity says 1 inverse square becomes 2 inverse squares. And inverse squares are exactly how light behaves in our problem. If the original light contributes 1 divided by its distance squared, then the 2 new lights contribute the inverse squares of their distances. And together, they add to exactly the original amount. 1 light becomes 2 with no change in what the observer receives. This construction is more than a geometric curiosity. It gives us an algorithm for replacing 1 light with 2. It is not specific to circles or even the Basel problem. Now our question is whether this same geometry is mysteriously hiding inside our expanding circle. Return to our snapshots from part 1. There we observed that consecutive snapshots aligned, although we postponed the reason why. For now, let's see what that alignment makes possible. It creates the right triangles we need. Begin with circle 16 and use it to build circle 32. Replace light plus 5 with the total brightness from 2 new lights. Draw a line from plus 5 through the center circle 32. Because it passes through the center, it is a diameter to circle 32. Place 2 new lights at its endpoints. Geometry is doing our work. The 2 new lights and the observer form a triangle where the longest side is a diameter. That is great news, but not new news, because more than 2,500 years ago, an ancient mathematician, Thales, proved that every triangle built on a diameter is a right triangle. So circle 32 created the right triangle we need. But we still have one missing piece. The original light must lie at the foot of the altitude to the hypotenuse. So overlay the previous snapshot and notice that the observer and circle 32 center are the endpoints of circle 16's diameter. And by Thales' theorem, again, the old light also lies on a right triangle. And this makes the segment from old light to observer perpendicular to the larger triangle's hypotenuse, revealing the exact geometry from part 3. Voila! Right triangles hiding between 2 circles. Apply the inverse Pythagorean identity. Brightness from the old light is replaced perfectly by the combined brightness from the 2 new lights. So light from plus 5 on circle 16 becomes the combined light from plus 5 and minus 11 on circle 32. And as the movie continues, plus 5 moves further from the observer. It keeps the light appropriate for its new distance and passes the rest forward, first to minus 27 and then to minus 59. Only the labels change. The geometry remains the same. The same local transfer applies to every odd light. Now that we've uncovered the hidden geometry between snapshots, let's return to the beginning and watch the entire movie unfold. Here's our first snapshot, circle 2. Since the circumference equals pi times the diameter is 2 divided by pi. Our original light sits exactly 1 diameter away from the observer, so the observer receives 1 divided by d squared, which simplifies to pi squared divided by 4 units of light. Pi squared divided by 4 is the amount of life that begins our proof. And now let the snapshots play. 1 becomes 2, 2 becomes 4, 4 becomes 8. As the circle grows and flattens, existing lights move further away while new lights appear. At every stage, the local geometric identity preserves total brightness. Together, these local identities produce a remarkable global picture. The circle approaches the number line, and every odd integer bearing light settles into its final position. The observer now receives light from every odd integer on the number line. And because every transfer preserved total brightness, that total remains pi squared divided by 4. Then by symmetry, half comes from the positive odd integers, pi squared divided by 8. And one algebraic step finishes our Basel problem. Let S be our sum over all positive integers. Separate S into odd and even terms. We know the odd part equals pi squared divided by 8. For the even part, notice that the denominator contains a factor 2 squared. Factor this constant. Now the series looks familiar. It is the sum of all positive integers, which is S. Substitute that infinite sum as S, and our equation simplifies to one variable, S. Solve for S to equal pi squared over 6, which is our solution to the Basel problem. But for me, solving the Basel problem was never the greatest joy. The real joy was discovering the architecture behind the answer. Each integer begins with more light than it has at its final position. And as the circle expands, distances from the observer increase, so the light observed decreases. As each light moves outward, its contribution decreases. Yet the geometry ensures that the difference reappears at a new light. Repeated across every snapshot, this leaves each odd integer contributing exactly the brightness required at its final position. And this happens only because several ideas work together. An expanding circle provides the architecture. Right triangles reveal the hidden geometry. The inverse square law gives us light, while the inverse Pythagorean identity preserves its total brightness. This is why I created this video. These ideas were not created for the Basel problem, yet together they reveal exactly the identity it was waiting for. This is one of my deepest joys of doing math. Beautiful ideas rarely live alone. They connect behind the scenes until together they reveal something bigger and more beautiful. In this proof, even the integers seem to participate, almost coming to life, each carrying light forward until the next generation is ready to receive it. Speaking of the integers, so far we've assumed that consecutive snapshots align integers perfectly. A diameter through an odd integer on the larger circle also passes through the corresponding integer on the previous snapshot. So why does this happen? The reason why comes from another beautiful circle theorem. Begin with circle 8. The integer is divided into 8 equal arcs. So the central angle between consecutive integers is 360 divided by 8, or 45 degrees. So we start by assuming the angle between 0 and 1 is 45. Now, double to circle 16. There are twice as many equally spaced integers, so the angle between consecutive integers is 22.5. To prove that the two copies of +1 align, we need to show that our construction produces exactly this angle. Because the two circles share the point 0 and circle 16 has twice the radius, the top of circle 8 is also the center of circle 16. And from that point, draw one segment to 0 and another to +1 on circle 8. These segments form an inscribed angle subtending the arc from 0 to 1. And by the inscribed angle theorem, this angle is half the corresponding central angle. Since the central angle of circle 8 is 45, this ensures the angle between 0 and 1 for circle 16 is 22.5, which matches the spacing between consecutive integers on circle 16. And therefore, the ray through +1 on circle 8 continues through +1 on circle 16. And the same reasoning works for every integer. For example, the central angle from 0 to 3 on circle 8 is 135 degrees. The corresponding inscribed angle is half that, which is precisely the direction of +3 on circle 16. So the integers do not line up because we carefully placed them there. Their alignment is forced by the inscribed angle theorem. And that alignment supplies the geometry required in part 4. Every old light lies on the diameter, joining its surviving copy to a newly created light. The inverse Pythagorean identity can then take over and pass the light forward. One theorem lines up the integers, and another shows them how to share the light.